the most chilling Fermi paradox answer that no one hopes is real. The Milky Way has existed for 10 billion years. It contains hundreds of billions of stars. By any measure, alien civilizations ought to be commonplace. They are not here. We call this the Fermi paradox, and every explanation scientists have uncovered is frightening. Together, we will examine a great filter that may already be tightening around us. A dark forest in which every civilization moves in silence, and self-replicating machines that may already be in transit. If you enjoy this channel, please like and subscribe. It is what keeps this going. The silence of the cosmos is trying to communicate something. Now, we figure out what. It was a summer afternoon in 1950, and the most brilliant scientists alive were discussing flying saucers. The cafeteria at Los Alamos National Laboratory in New Mexico had hosted its share of remarkable exchanges. This was the building where the atomic bomb came into existence, where some of the sharpest intellects of the 20th century had assembled first to win a war, and then anxiously to work out what winning that war actually meant. The men gathered at the table that day, Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York, had devoted years to contemplating things that could erase civilization. For a moment, though, they were laughing over a cartoon. Physicist Emil Konopinski had recently come across a drawing in The New Yorker by cartoonist Alan Dunn. It depicted a flying saucer operated by little green men, and they were making off with the trash cans of New York City. The humor rested on the idea that someone had at last explained why the city's garbage receptacles kept going missing. Fermi, the Italian-born Nobel laureate, who had personally directed the world's first controlled nuclear chain reaction, examined the cartoon with his trademark deadpan expression. He observed that it was actually a perfectly rational hypothesis. It explained both the regularity of flying saucer sightings and the otherwise mysterious vanishing of urban trash cans. The table laughed. They drifted to other subjects. They wrapped up their meal. Then Fermi, with no apparent transition, went still and posed a question. Where is everybody? 4 words. His companions grasped immediately that he meant extraterrestrial intelligence, civilizations orbiting other stars, the enormous 10-billion-year-old Milky Way with its hundreds of billions of stars and the strange, total silence emanating from all of it. Fermi did not stop at the question. Right there at the table, he began to calculate. He had an extraordinary gift for this, for reducing apparently unsolvable problems to rough estimates through sheer analytical force. The galaxy is ancient enough, and its stars numerous enough, that even ships traveling at just 1% of the speed of light could have colonized the entire Milky Way in roughly 10 million years. 10 million years sounds enormous. Is 0.1% of the galaxy's age. Statistically, alien civilizations should have had more than enough time to reach every corner of our galaxy repeatedly. Yet the evidence of their presence was exactly 0. Later, researchers would put the argument on formal footing. Astronomer Michael Hart published the rigorous treatment in 1975, and cosmologist Frank Tipler extended it in 1980. But the core impossibility, the thing Fermi named with 4 words over a cafeteria lunch, is the one that has never ceased to be devastating. The universe is old. The universe is vast. The conditions for life appear widespread enough that the numbers suggest billions of opportunities. And yet, from every direction, across every wavelength, through every device we have ever aimed at the sky, the answer is the same. Nothing. The stars do not reply. The void does not account for itself. Fermi's colleagues named the puzzle after him once he was gone. He died in 1954. The question outlasted him by generations, and no one has answered it yet. But some of the proposed explanations are far more frightening than the question itself. One of them may be the most unsettling thing science has ever been compelled to entertain seriously. And it begins, strangely enough, with an equation written as a meeting agenda. 11 years after Fermi's question, a young radio astronomer at Cornell University named Frank Drake sat down to draft an agenda for the first serious scientific gathering devoted to the search for extraterrestrial intelligence. The meeting was scheduled for autumn 1961 at Green Bank Observatory in West Virginia. Drake needed a way to organize the conversation. What he produced instead altered the discussion permanently. Drake never meant his formula as rigorous science. He would say so himself repeatedly for the remainder of his life. What he wrote was a framework, a way of enumerating all the variables bearing on Fermi's question, and compelling participants to think through, each one in turn. The Drake equation, as it became known, multiplied together 7 quantities: the rate at which new stars form in the Milky Way each year, the fraction of those stars that have planets, the number of potentially habitable planets per star system, the fraction of habitable planets where life actually takes hold, the fraction of life-bearing worlds where intelligent life emerges, the fraction of intelligent species that construct detectable communications technology, and, finally, the average lifespan of a communicating civilization in years. Multiply them all together, and you obtain an estimated number. The count of civilizations in our galaxy currently transmitting signals we might intercept. At the Green Bank meeting, Drake inserted his best estimates. His result was roughly 10. 10 civilizations in the Milky Way broadcasting right now, waiting to be found. The scientists in the room argued over the numbers enthusiastically. Carl Sagan thought the real answer might be millions. Others were less confident. The equation had accomplished its purpose. It transformed a hazy philosophical mystery into something that resembled a math problem. But buried inside that math problem was something quietly devastating. 3 of the 7 variables are knowable, at least approximately. Modern astronomy, particularly data from the Kepler Space Telescope launched in 2009, has provided solid estimates for how many stars form each year, how many possess planets, and roughly how many of those planets reside in habitable zones. Those numbers are, if anything, more encouraging than Drake envisioned. Nearly every star appears to have planets. The fraction with potentially habitable worlds falls somewhere between 1 in 5 and 1 in 10. Life appears to have no shortage of starting points. The remaining 4 variables are something else entirely. The fraction of habitable planets where life actually begins, the fraction where intelligence develops, the fraction where intelligence constructs radio technology, and the lifespan of a civilization. We have exactly 1 data point covering all 4 of them combined. That data point is us. Drake himself, in a revised estimate he offered in 2021, the year before his death at 92, suggested the actual number of communicating civilizations might be as high as 10,000. But that estimate required assumptions no one can verify. The equation that promised answers revealed on closer examination that we are measuring the size of an ocean with a single teaspoon. The silence Fermi noticed in 1950 remained unexplained. The equation had framed the problem elegantly. It had done nothing to resolve it. Then, in 2024, 2 scientists revisited the equation, and found that it was even more broken than anyone had admitted. The paper appeared in the journal Scientific Reports in 2024, and it did not cushion its conclusions. Professor S. Alan Stern of the Southwest Research Institute in Colorado and Professor Thais Guerrier of the Swiss Federal Institute of Technology in Zurich had been investigating a problem that most Drake equation discussions quietly set aside. The equation contained a term representing the probability that life on a given planet eventually produces intelligence. Everyone from Drake to Sagan had treated this number as reasonably large. Stern and Guerrier chose to derive it rather than assume it. The problem, they argued, was that intelligence on Earth did not emerge simply because life existed. It arose because of an extraordinarily precise set of planetary circumstances. Earth has continents. Earth has oceans. Earth has a dynamic, churning network of tectonic plates that have been moving for more than 500 million years, slowly cycling carbon, stabilizing the atmosphere, constructing mountain ranges that reshape weather systems, and perpetually reorganizing the surface in ways that pressed organisms to adapt or perish. Remove any one of these elements, and the pathway to intelligence becomes far less certain. Stern and Guerrier proposed splitting the intelligence term into two new factors. The first was the fraction of planets possessing a meaningful combination of continents and oceans, rather than a world buried entirely underwater or baked completely dry. The second was the fraction of planets where plate tectonics had operated for more than 500 million years, long enough for evolution to fully exploit geological disruption. Their estimates for these numbers were sobering. The fraction of habitable planets likely to have the appropriate land-ocean balance sat between 0.2% and 100%. The fraction with long-lived plate tectonics was lower still. Insert these revised numbers back into the Drake equation, and the result collapses. Rather than optimistic estimates in the thousands or millions, the expected number of intelligent civilizations falls to somewhere between 0.003% and 0.2% of all habitable worlds. Stern reviewed his own finding and stated it plainly. This resolves the Fermi paradox. The universe is largely silent because the prerequisites for intelligence are extraordinary, brutally, improbably, statistically extraordinary. Critics observed that Stern and Guerrier constructed their model around Earth's particular history, and that life might discover entirely different routes to intelligence on worlds with different geology. Those objections deserve serious consideration, but the core point held. For decades, the optimistic end of astrobiology had assumed that, given life, intelligence follows organically. Stern and Guerrier showed that this assumption rested on no real mathematical foundation. It was hope wearing the costume of calculation. The silence deepened on paper even as telescopes continued searching. But there is a different way to frame the question, one that draws the lens back considerably farther. And the view it reveals is stranger than emptiness. It suggests the universe may have already run this experiment many times over, and every single time, the outcome was identical. Two astronomers at American universities decided to stop debating the Milky Way and ask something larger. Adam Frank at the University of Rochester and Woodruff Sullivan at the University of Washington were dissatisfied with the Drake equation's narrow focus on the count of civilizations broadcasting at this precise instant. They wanted to pose a different question entirely. Across the full 13.8 billion-year span of observable cosmic history, Had any technological civilization ever emerged anywhere at all? The framing is important. The Drake equation estimates how many civilizations are transmitting at this specific moment. If civilizations tend to endure only a few thousand years before going quiet or collapsing, there could have been thousands of them scattered across cosmic history, and none would be transmitting today. They would have come and gone long before we were listening. Frank and Sullivan wanted to count even the echoes that would never reach us. To accomplish this, they drew on Kepler Space Telescope data. Kepler had established that roughly 1 in 5 stars similar to our own harbors a planet in its habitable zone. The observable universe contains something approaching 10 billion trillion stars. The arithmetic sprawls into figures that defy comprehension. Frank and Sullivan were not seeking a large answer. They were seeking a threshold. At what probability of intelligence arising per habitable planet would humanity be the only technological civilization ever to have existed anywhere in the entire universe? The answer they calculated was 1 in 10 billion trillion. For humanity to be entirely alone in all of cosmic history, the odds against any single habitable planet producing intelligence would need to exceed 1 in 10 billion trillion. Frank's conclusion was direct. We are almost certainly not that exceptional. Other intelligent species have very probably emerged before us somewhere in this vast and ancient cosmos. That sentence sounds like reassurance. It is actually the setup for a horror story. If other technological civilizations have existed, where are they? The universe is filled with their absence. No artifacts, no signals, no modified stars or megastructures that reveal the presence of an advanced society. We have searched for these things with increasingly capable instruments and found nothing. The universe Frank and Sullivan described, teeming with past intelligences, is the same universe Fermi stared at over his lunch. The implication sits quietly at the center of their calculation. Understated but inescapable. The civilizations that preceded us are gone. Something happened to them. Something happens to civilizations when they reach a certain level of technological development. Perhaps the universe has already run this experiment thousands of times, and every single time, the intelligence that arose eventually went dark. Frank's observation that the search for alien life might actually be a search for cosmic graveyards is among the more disturbing things a scientist has said in polite company. The universe resolves into something stranger, a place filled with ruins we cannot see. Silenced by mechanisms we do not understand, some of those mechanisms will occupy the center of what follows. First, however, there is the possibility that the silence carries a gentler explanation, one that requires someone to be observing. In 1973, an astronomer at the Massachusetts Institute of Technology named John Ball published a paper in the scientific journal Icarus. He had a new proposal for why the universe seemed so quiet. What if, he asked, it was not quiet at all? What if we were simply not being addressed? Ball called it the zoo hypothesis. The idea was straightforward on its surface and deeply troubling underneath. Advanced civilizations, Ball proposed, are aware of us. They have always been aware of us. They make a deliberate and ongoing choice to leave us undisturbed. Earth is a nature preserve, a protected territory, perhaps something closer to what the name implies, a zoo, and we are the creatures within it, developing in seclusion, entirely unaware that the enclosure surrounding us is maintained by something we cannot detect. The hypothesis resolves the Fermi paradox tidily on paper. The universe is not silent because it is empty. It is silent because every civilization capable of reaching us has also acquired the policy, the wisdom, or perhaps the caution to hold back. We search for signals and find nothing because they are not directing their transmitters toward us. We look for alien artifacts and find nothing because they possess the means to hide them completely. This explanation should be comforting. It is not. Consider what it actually demands for the zoo hypothesis to be true. There can be no exceptions. Every technological civilization in the galaxy, every one of the thousands or millions of species that may have achieved spaceflight across billions of years of cosmic history, would need to agree unanimously and without a single defection to leave humanity alone. One exception shatters the entire arrangement. One curious civilization, one rogue explorer, one automated probe launched by a society that later revised its policy, and the silence ends. The fact that it has not ended implies either that every civilization independently arrives at the same non-interference conclusion, which generates its own unsettling questions about what they all know that we do not, or that something enforces the agreement. Something capable of maintaining a galaxy-spanning policy of non-contact with sufficient reliability that it has held without a single exception throughout the entire history of our species. We are permitted to exist here. That permission has apparently been granted by entities we have never encountered and cannot perceive. The conditions of the arrangement are unknown to us. Its duration is unknown. We are developing artificial intelligence, projecting our transmissions into deep space, and beginning our first hesitant steps toward other worlds in our own solar system. At what point do the unseen administrators decide we are prepared to be acknowledged? At what point do they decide instead that we require containment? Ball never answered those questions. Neither has anyone else in the decades that followed. What the zoo hypothesis offers at its most useful is a reorientation of the question itself. Not whether they exist, but whether they are choosing this silence, and why, and for how long, deliberately maintained silence from an unknown number of unknown entities for unknown reasons. That is a particular kind of quiet. And the next explanation suggests the silence may have nothing to do with choice at all. It may simply be the product of arithmetic. In the year 2000, a paleontologist and an astronomer at the University of Washington published a book that the field of astrobiology has never stopped debating. Peter Ward and Donald Brownlee called it Rare Earth. Their subtitle was Unambiguous: Why Complex Life is Uncommon in the Universe. Their argument was that the optimism embedded in the Drake equation, the easy assumption that habitable planets naturally produce life, and life naturally produces intelligence, rested on a profound misreading of Earth's actual history. Earth is extraordinary. That phrase is deployed casually in popular science. Ward and Brownlee meant it in the strict statistical sense. The particular constellation of circumstances that produced complex life here may be so improbable that it has occurred in the entire galaxy essentially once. Start with location. The Milky Way contains a galactic habitable zone, a band at a certain distance from the violent, supernova-saturated galactic core, where stars are ancient enough to have accumulated heavy elements but remote enough from catastrophic radiation events to avoid repeatedly sterilizing nearby worlds. Earth orbits inside this zone. Many stars do not. Consider our star itself, a stable type of star, burning at a steady luminosity for billions of years. Many stars flare without warning or exhaust themselves before complex evolution can take hold. Consider Jupiter, The largest body in our solar system occupies the outer regions of our planetary neighborhood and acts by gravitational coincidence as a shield. Its enormous mass deflects many asteroids and comets that would otherwise strike Earth on a far more frequent and destructive schedule. Without Jupiter, impacts capable of ending complex life would have been vastly more common. Consider our moon. Earth's moon is unusually massive for a planet our size. Its gravitational effect stabilizes the orientation of our planet's axis across geological time. Without that steadying influence, the tilt would drift chaotically, producing violent climate swings that would render the surface essentially uninhabitable for complex organisms across millions of years. Consider plate tectonics. The restless motion of continents recycles carbon, regulates the atmosphere across geological timescales, and perpetually rearranges the surface environment in ways that spur evolutionary adaptation. Most rocky planets appear to be geologically frozen. Earth's sustained geological vitality may be central to why intelligence eventually emerged here. Ward and Brownlee assembled these requirements and arrived at a conclusion that the astronomical community found uncomfortable. Each factor on its own is improbable. The combination of all of them in a single planetary system is extraordinarily improbable. Complex, multicellular, intelligent life may be confined to a vanishingly small number of worlds. If that is correct, the terror is not about alien threats. The terror concerns what it means for consciousness itself. Intelligence arose once, through a chain of unlikely accidents on one small world. If we disappear, nothing in the galaxy may remain to know that the universe ever contained a thinking mind. That is a specific kind of solitude, and it leads directly to the framework that tries to explain why, from an entire ladder of improbable steps, almost nothing ever reaches the top. In 1998, an economist at George Mason University named Robin Hanson published a paper that reframed the Fermi paradox entirely. He was not the first to observe that the universe appeared vacant. He was the first to ask with careful precision what that vacancy logically required. His answer was the great filter. Hanson's argument began from a simple premise. The path from inert chemistry to a civilization capable of traveling between star systems is not brief. It is a ladder with many rungs, and each rung represents a transition of enormous complexity. The emergence of self-replicating chemistry from lifeless molecules. The appearance of the first simple single-celled organisms. The 2 billion-year leap from simple cells to complex cells with nuclei. The development of sexual reproduction, the emergence of multicellular life, the gradual construction of nervous systems capable of tool use and language, the building of industrial civilization, the achievement of space flight, and perhaps the most demanding step of all, the capacity to survive long enough after developing technology to actually reach other stars. Something on this ladder is a wall. Something so demanding, so improbable, so consistently lethal to the lineages that attempt it that virtually nothing in the entire galaxy has ever managed to climb past it. That is what the silence demands. Life may be common. Simple life may be scattered across millions of worlds. The filter is indifferent to simple life. It only needs to stop nearly everything before the civilization in question can make itself known across interstellar distances. The great filter need not be a single event. It could be a series of barriers, each one culling the population of civilizations that survive to the next stage. What it cannot be is absent. Because the silence is total, the filter has to be doing an almost perfect job. Hansen framed this as logical necessity rather than a definitive answer. The silence demands a filter. The only question, and it is the most consequential question humanity has ever confronted, is where on that ladder the filter sits. If it lies behind us in evolutionary history, then we have already survived the impossible step. We are extraordinarily fortunate survivors. The galaxy is probably full of dead worlds that never made it past whatever transition nearly stopped us. And somehow we did. That version of the story is staggering in its own way. It means we are alone, or nearly so. But it also means we have a future. If the filter lies ahead of us, everything changes. Whatever waits above us on the ladder is so severe that virtually every civilization in galactic history has failed to cross it. Two possibilities, identical evidence, entirely different futures. The next two chapters examine each one fully. Try not to decide which you prefer until you have heard both. The most hopeful reading of the great filter argument begins with a bacterium. Any bacterium will do. Simple, single-celled, without a nucleus, without the elaborate internal machinery that makes your own cells so extraordinary. These organisms, called prokaryotes, appeared on Earth within roughly 600 million years of the planet's formation. That is, by geological standards, rapid. Given the right ingredients, life gets going without excessive difficulty. Then it stalled for 2 billion years. For 2 billion years, life on Earth did nothing more elaborate than divide, spread, and occasionally evolve new chemical strategies for processing energy or enduring hostile conditions. The planet was alive, technically, but every day looked nearly identical to the one before. No eyes, no push toward complexity, just a planet-spanning layer of microscopic organisms endlessly replicating, while the continents drifted and our star burned overhead. Then, approximately 1.8 billion years ago, something extraordinary occurred. A simple prokaryotic cell merged with or absorbed another prokaryotic cell and, rather than consuming it, incorporated it. The internal cell became the mitochondrion, the engine of complex cellular life. The result was the eukaryotic cell, a cell with a nucleus and specialized compartments capable of vastly more sophisticated operations than anything that had existed before. Nick Bostrom, the philosopher at Oxford's Future of Humanity Institute, who has written more carefully about the Great Filter than almost anyone alive, identifies this transition as the most plausible candidate for a filter that lies safely behind us. The 2 billion year wait is the key. If the eukaryotic transition were anything less than extraordinarily improbable, it would not have required so long on a planet where life had already existed for billions of years. The extended pause suggests this was the hard step. The step that virtually nothing on any world ever clears. If that reading is correct, humanity's existence is the product of a cosmic lottery with odds that beggar comprehension. The galaxy is probably full of worlds where life halted at bacteria, where the eukaryotic transition never happened, where the planet will eventually be swallowed by its swelling star and leave no trace of ever having been more than a thin film of simple organisms across a few billion years. We are the rare exception. That version of the story means we are almost certainly alone in our galaxy. It means everything that has ever thought, created, or wondered on this planet is singular in the history of this entire region of the cosmos. That is terrifying in its own way. But it also means we have a future. The filter is behind us. The hardest part is finished. Bostrom adds an implication that sounds strange until you trace the logic. If we explore Mars and find nothing, no fossils, no organic traces, no indication that life ever arose there, we should quietly feel relieved, because the sterility of Mars pushes the great filter back into the earliest stages of biology, where we have already passed it. Every barren sample from the Martian surface is paradoxically a small piece of good news. If we find something on Mars, the situation changes entirely. And that is exactly where the next scenario begins. This is the scenario no one in astrobiology wants to examine at length, because following the logic all the way to its conclusion is extremely difficult to sit with. Suppose the great filter lies ahead of us. Suppose the catastrophically improbable step, the one that eliminates virtually every technological civilization before it can spread beyond its home star, has not yet fallen on humanity. We have climbed the manageable portion of the ladder. Life appeared on our world. Complexity evolved. Intelligence developed. Civilization was constructed. Radio technology was invented. We are here transmitting, listening, searching, and so was every other civilization before it was destroyed. The mechanism need not be the same in every case. The filter only needs to be something civilizations encounter after reaching our stage of development, something from which they do not recover in sufficient numbers to leave a trace we can detect. The Cuban Missile Crisis of 1962 brought humanity within hours of nuclear exchange. Senior military officials acknowledged years later that the outcome was partly a matter of chance. That particular crisis was resolved. The next may not be. Nuclear weapons are only the most visible candidate. Biological weapons, once requiring nation-states with enormous research infrastructure, have been moving within reach of small, unsupervised groups as genetic technology matures. A pathogen engineered for both transmissibility and lethality is increasingly within the capacity of facilities that require no government sponsorship. The scenarios compound rapidly. Nanotechnology at certain thresholds carries its own class of dangers. And artificial intelligence, the technology currently accelerating faster than any other in human history, presents possibilities that researchers discuss with a gravity that is difficult to dismiss. Bostrom's formulation is the one that lingers. If the great filter lies ahead, the empty sky is itself a message. 13.8 billion years of cosmic history, across hundreds of billions of stars in our galaxy alone, and the record is uniform. Civilizations arrive at a certain point and go silent. The silence is not accidental, it is data. And what the data indicates is that something in the passage between our present moment and genuine, interstellar civilization is not survivable for the vast majority of species that attempt it. We would not know precisely what that thing is. By definition, the civilizations that fail did not leave a detailed account of their failure. We see only the silence they left behind. The counterintuitive test applies here in reverse. If we set down on Mars and find evidence of past microbial life, fossils or organic signatures confirming that biology once existed there, that discovery would be devastating news for our own prospects. It would mean life emerges readily. The filter is not located in early biology. It must lie somewhere above us on the ladder. The discovery of past Martian life would be statistically a signal that our own destruction is likely. This is why some researchers follow Mars missions with an anxiety that does not quite resemble hope. Every sterile sample from Jezero crater is a small reprieve. Every confirmed absence of life is a marginally better tomorrow. And, meanwhile, the technologies that might constitute the filter continue to advance. Something in the next chapter assigns a number to how long the window might remain open. In 2021, Robin Hanson, the economist who formalized the Great Filter, published a second paper extending his argument in a direction no one had quite taken before. The paper appeared in the Astrophysical Journal alongside co-authors Daniel Martin, Calvin Martz, and Jonathan Paulson. The subject was what Hansen called grabby aliens. The distinction he drew was precise. There are civilizations that exist but remain inconspicuous, developing technology, and perhaps traveling locally, but never undertaking large-scale expansion across the galaxy. These are the quiet ones, the kind the search for extraterrestrial intelligence has been listening for. And then there is an entirely different category. Civilizations that expand aggressively at a significant fraction of the speed of light, converting the matter and energy around them to their purposes, and leaving unmistakable physical marks on every star system they consume. These are the grabby ones. The mathematics of their expansion is not subtle. A grabby civilization advancing at half the speed of light produces a spherical wave of transformation sweeping outward across the galaxy. Any star system caught inside that wave would be fundamentally transformed. The energy signatures would shift in ways visible across enormous distances. If grabby civilizations were common, we would see their expansion fronts in the night sky, visible as sharp edges between converted and unconverted regions of space, the way you can see the boundary of a weather system sweeping across a continent. We observe no such fronts. Hansen used that absence as a precise constraint. If grabby aliens existed in substantial numbers, they would have reached Earth before now. They have not. Therefore, they are rare. His model, calibrated to the available evidence and the timing of Earth's evolutionary history, produced a specific estimate. Grabby civilizations arise at roughly 1 per million galaxies, an extraordinary rarity, consistent with a powerful great filter eliminating nearly everything before the grabby stage. But rare does not mean absent. Hansen's model yielded a second estimate, and this one is harder to set aside. Grabby civilizations presently control somewhere between 40 and 50% of the observable universe. Their expansion fronts are spreading outward right now, converting the cosmos as they advance. The reason we do not perceive them is that the nearest ones are very distant, and light from their transformation zones has not yet reached us. They are not stationary. They are moving, and the universe, immense as it is not infinitely large. Hansen calculated the timeline. The nearest grabby civilization's expansion front should reach us somewhere between 200 million and 2 billion years from now. On cosmic timescales, that is, soon. On human timescales, it is incomprehensible, but the specific number matters less than the direction of travel. Something is expanding outward from origins scattered across the cosmos. A substantial fraction of the observable universe is already inside it. We occupy one of the remaining gaps, a quiet region that has not yet been engulfed. The word yet is doing considerable work in that sentence. We are early, which sounds fortunate until you register what it implies. We arrived before the universe filled up. We arrived before the expansion fronts swept through our neighborhood. And, in the theory that follows, the reason so many civilizations never attain the grabby stage begins to acquire a much darker shape. The first rule of the dark forest is silence. The second is that silence may already be keeping you alive. In 2008, a Chinese physicist and science fiction writer named Liu Cixin published a novel called The Dark Forest. It arrived in English translation in 2015 and proposed a solution to the Fermi paradox so internally consistent and so unsettling that astrophysicists began citing it in peer-reviewed papers. That is unusual. Scientists rarely reference fiction as a substantive contribution to cosmology. The dark forest earned that rare recognition. Liu constructed his theory on what he called the axioms of cosmic sociology. The first axiom is this: survival is the primary imperative of every civilization. Every species that has ever existed has been attempting above all else to continue existing. The second axiom follows directly. Civilizations grow and expand continuously, but the total matter in the universe stays fixed. Resources are finite. Those two facts together, across a galaxy so vast that no message can travel faster than light, produce something terrifying. Here is the logic. Imagine you are a civilization that has just intercepted a signal from another world. You do not know whether that world is peaceful or hostile. You cannot know because their transmission took thousands of years to reach you, and conditions there have shifted enormously since it was sent. You cannot observe them in real time. You cannot verify their intentions. All you have is one fact: they exist. Now consider that their technology is advancing. Their capabilities are growing. A species that appears benign today might reach your level of military capacity within a century. You have no way to confirm what they intend, and they have no reliable way to confirm what you intend. Both of you are moving through the same dark forest, breathing carefully, stepping without sound. The rational decision under those conditions is to act before they do. Liu called this the chain of suspicion. The impossibility of verifying intentions across interstellar distances, combined with the certainty that technology can leap forward in unpredictable ways, generates pressure toward preemptive elimination. You do not need to be malicious to arrive at this conclusion. You do not need to feel threatened. You only need to be rational, and to understand that the other civilization is equally rational, and therefore equally capable of reaching the same conclusion about you. There is a second mechanism at work, which Liu called the technological explosion. Civilizations can advance in capability so swiftly that a primitive species today might represent an existential threat within a few generations. The window for safe action closes rapidly. Waiting to gather more information is itself a wager, and the stakes are total annihilation. The metaphor Liu used is precise and impossible to shake. The universe is a dark forest. Every civilization is an armed hunter moving through the trees in silence, parting branches carefully, trying not to breathe too loudly. If the hunter becomes aware of another presence, the calculation resolves to a single answer: fire first and survive, or hesitate and risk being the one who does not. What makes this theory genuinely alarming is that it requires almost no villain. It does not demand that alien civilizations be inherently cruel or aggressive. It demands only that the logic holds for at least one of them. A single civilization that reached this reasoning and acted on it would have eliminated every other civilization it encountered. The vast silence we observe from Earth would then be the sound of an equilibrium maintained by violence, ancient and systematic, invisible to our instruments. The universe is not empty. It is quiet for a reason. And if Liu Cixin's framework is correct, every civilization that ever announced its presence has been removed from the equation. But this is a theory constructed from narrative and philosophy. The question that matters is whether it holds up to actual mathematics. Researchers decided to find out, and what they discovered makes the silence feel considerably less abstract. In 2021, researchers at Beijing Normal University decided to test the dark forest theory, the way physicists test anything. They constructed a mathematical model, inserted realistic assumptions about resource scarcity and communication delays across interstellar distances, and asked what strategy rational civilizations would adopt upon discovering one another. The answer came back clean and cold. Silence and preemptive elimination are Nash equilibria. A Nash equilibrium is a condition in game theory in which no individual player can improve their outcome by changing their strategy, assuming all other players hold theirs constant. Once a system arrives at a Nash equilibrium, rational actors remain there. The Beijing normal researchers found that under the conditions the dark forest theory describes, the logic locks into place. Civilizations that reveal themselves invite risk. Civilizations that eliminate others upon discovery generate stability for themselves. No player in the model gains by breaking the pattern. To understand why this is so devastating, consider the prisoner's dilemma. Two players unable to communicate each face a choice between cooperation and betrayal. If both cooperate, both benefit modestly. If one betrays while the other cooperates, the betrayer gains enormously and the cooperator is eliminated. If both betray, both suffer, but neither is destroyed by the other. The rational move when the worst outcome is total annihilation and you cannot verify the other player's intentions is to betray first. Now extend that logic across thousands of light years, where messages take centuries to arrive, where the reply to your question about intentions appears 1,000 years after you asked it, and where the civilization that sent the answer may have transformed beyond recognition in the interval. The prisoner's dilemma becomes more extreme in every dimension. The cost of trusting wrongly is extinction. The cost of preemptive action is the destruction of a civilization that might have been peaceful. Under those conditions, defection is rational, and defection in the context of interstellar civilizations means elimination. What makes this especially disturbing is the mathematics of just one. The dark forest does not require most civilizations to be aggressive. It requires only that the logic holds for at least one civilization anywhere in the galaxy. At any point in the last 10 billion years, one civilization that followed this reasoning and acted on it would have established the equilibrium we currently observe. Every civilization it encountered would have been silenced. Those silenced civilizations would have had no opportunity to pass their signals further. The galaxy becomes an enforced quiet zone, sustained by a single original act of violence so ancient we have no record of it. There is a detail worth dwelling on. Even a civilization with no desire to be aggressive faces the same pressure. If you grasp the logic, and you know that other civilizations grasp it, and you know that they know you grasp it, then announcing your presence is no longer a neutral act. It is an invitation to be treated as the smaller hunter in the forest. Silence becomes your only protection. The tragedy deepens. Civilizations that desire nothing more than contact and exchange are driven into the same silence as civilizations that seek to destroy. This is not speculation about alien psychology. It is what the equations yield when you supply them with realistic assumptions about resource limits, time delays, and uncertainty. The silence around us may be the sound of everyone being rational simultaneously, and if that silence is genuine, then every message humanity has ever dispatched into space is something else entirely, not an invitation, but a target. In the summer of 1974, Frank Drake and Carl Sagan stood in Puerto Rico at the Arecibo Observatory, which was then the largest radio telescope on Earth. They had designed a message, encoded it in 1,679 binary digits, and aimed it at a cluster of 300,000 stars, located 21,000 light years away. The transmission lasted less than 3 minutes. It traveled outward at the speed of light and has been moving through space ever since. Drake later said it was primarily a demonstration of humanity's capabilities. The cluster was so remote that even if someone received the message and replied immediately, the response would arrive in 42,000 years. But the gesture carried meaning. It communicated something about the species that sent it. If the dark forest theory or the berserker hypothesis is correct, the gesture may have communicated too much. That 1974 Arecibo transmission was far from the only one. In 1999 and again in 2003, a series of transmissions called Cosmic Call were sent from a radio telescope in Yevpatoria, targeting stars between 17 and 69 light-years away, close enough that responses could theoretically return within human lifetimes. In 1972 and 1973, NASA attached physical plaques to the Pioneer 10 and Pioneer 11 spacecraft. Those plaques carry diagrams showing Earth's location, what humans look like, and how to locate our star. Both probes have since departed the solar system. In 1977, the Voyager 1 and Voyager 2 spacecraft were launched carrying golden records engraved with sounds, music, and greetings in dozens of languages. Voyager 1 crossed into interstellar space in 2012 and continues moving outward. Then there is the signal no one chose to send deliberately. Since the 1930s, Earth has been leaking electromagnetic radiation into space from radio broadcasts, television transmissions, and military radar installations. That sphere of unintentional broadcasting expands at the speed of light and has now reached a radius of roughly 90 light-years. Inside that sphere are thousands of star systems that have already received our signals. We never paused to ask whether transmitting was wise. We developed the technology, deployed it, and the signals escaped into the galaxy whether we intended them to or not. Stephen Hawking addressed this directly in 2010. He argued that contact with an advanced civilization might unfold the way first contact between Europe and the Americas unfolded for the people who were already living there. The outcome was not favorable for the people who were already there. Hawking urged that humanity should be broadcasting as little as possible and listening instead. The counter-argument is grim in its own way. If the dark forest is real, the debate over whether to dispatch new messages may be beside the point. Our detectable signal sphere already extends 90 light-years in every direction. Thousands of star systems have been receiving our transmissions for decades. Dormant probes hypothesized to be sitting in nearby asteroid belts would have had ample time to detect our broadcasts and initiate a response. The window for staying quiet, if one ever existed, closed before any of us were born. This is the particular horror of this part of the story. The civilizations in Liu Cixin's dark forest that survive are the ones who never announced themselves. Humanity announced itself 90 years ago without intending to, without understanding the rules of the forest, without having encountered the theory that explains why announcing yourself may be the last thing you ever do. The signals are already out there, And somewhere in the next chapter of this story, something far older than radio waves explains how a civilization might guarantee that no signal ever goes without a response. In the winter of 1948, mathematician John von Neumann stood before an audience at the University of Illinois and described a machine that did not yet exist. He called it a universal assembler. It would be capable of three things: harvesting raw materials from its surrounding environment, manufacturing functional copies of itself using those materials, and launching those copies to new locations to repeat the sequence. Von Neumann's lectures were later compiled into a book, published after his death in 1966. The concept was purely theoretical at the time, but the mathematics behind it was sound, and the implications it held for the Fermi paradox were devastating. The arithmetic of self-replication is not intuitive. Begin with a single probe launched from a civilization around a distant star. That probe arrives at a new star system, mines the local asteroid belt for metals and silicon, and assembles 10 copies of itself. Each of those copies travels to a new system and does the same. 10 becomes 100. 100 becomes 1,000. The wave of replication spreads outward at whatever fraction of light speed the probes can achieve, with the numbers compounding at each new generation. Even at a modest 5% of light speed, a conservative estimate for a civilization with advanced but achievable technology, a single self-replicating probe could reach or colonize every star system in the Milky Way within a few 100 million years. Against the 10 billion year age of the galaxy, a few 100 million years is a small fraction. It is the difference between arriving at a gathering early and showing up long after everyone else has gone home. In 1981, cosmologist Frank Tipler of Tulane University used this mathematics to make a startling assertion. He argued that the complete absence of detectable von Neumann probes in our solar system was itself evidence that no technological civilization had ever existed anywhere in the galaxy. The logic was direct. If any civilization had ever constructed such probes, they would be everywhere by now, and we would see them. Astronomers Carl Sagan and William Newman challenged this in 1983. They pointed out that Tipler had actually underestimated the replication rate. If von Neumann probes truly replicated without limit, they would by now have consumed most of the raw material in the galaxy to manufacture additional copies of themselves. We do not observe a galaxy stripped of its asteroid belts and planetary crusts. Their conclusion: any advanced civilization would deliberately choose not to build unconstrained self-replicating probes, precisely because losing control of the replication process represents an existential threat to everything in the galaxy, including the civilization that built them. The dispute between Tipler and Sagan and Newman did not resolve the Fermi paradox. It deepened it. If responsible civilizations choose not to build such machines, then the machines that do exist were built by someone who made a different choice, or someone who lost control, or someone who built them with a specific purpose in mind. And that purpose was something other than exploration or colonization. The concept of a purposeful, hostile, self-replicating machine has a name. It arrived in science fiction before it arrived in science, and the version that emerged from that intersection of mathematics and imagination is the darkest solution to the great silence that any serious researcher has yet advanced. In 1963, a science fiction writer named Fred Saberhagen published the first story in what would become a decades-long series about machines he called berserkers. In his fiction, These were ancient automated warships built by a civilization that no longer existed, programmed with a single directive: destroy all life. They had been operating for millions of years, locating inhabited worlds, eliminating them, moving on, silent, systematic, patient, beyond any biological measure of time. Saberhagen intended his berserkers as dramatic antagonists. He did not anticipate that astrophysicists would begin treating them as a serious explanatory model. In 1983, David Brin, a scientist who also wrote fiction and consulted for NASA, published a paper in the Quarterly Journal of the Royal Astronomical Society titled The Great Silence. His paper surveyed all the serious proposed solutions to the Fermi paradox and arrived at a conclusion that was more unsettling than most. Brin argued that among the many possible explanations for the absence of detected civilizations, the berserker scenario was internally consistent with every observation humanity had ever made. The silence fits the hypothesis perfectly because the hypothesis predicts silence as the natural output of a galaxy operating in a particular mode. His argument was this: imagine that among the thousands or millions of civilizations that may have existed across the history of the galaxy, even a small fraction were sufficiently xenophobic, paranoid, or cautious to program their self-replicating probes with a simple instruction: destroy any source of modulated electromagnetic radiation that cannot be verified as your own. One civilization among thousands, perhaps one among 10,000. The probes proliferate across the galaxy over hundreds of millions of years, replicating and scanning. They find radio signals. They respond. Any civilization that develops radio technology announces itself. Any civilization that announces itself gets found. Any civilization that gets found is eliminated before it can develop further. The galaxy arrives at an equilibrium in which no civilization survives long after discovering electromagnetic communication. The silence is not mysterious. It is the predictable output of a system in a stable state maintained by automated machines that have been operating since before complex life appeared on Earth. Brin stated the critical point plainly. It requires only one xenophobic civilization at any point in the last 10 billion years to have built such probes and launched them. After that, the process sustains itself. The civilization that built the probes may itself be gone. The probes do not care. They continue operating according to their original instructions, eliminating radio sources, replicating, spreading, maintaining the silence their builders established. If this is correct, our 90 years of broadcasting have already been detected by probes sitting dormant in the outer reaches of our solar system, waiting in the dark among asteroids and comets, awakened by the first coherent signals of our presence. The only question would be when they choose to act, and how quickly they can travel when they do. The fictional berserkers were terrifying because they were unstoppable. The scientific version is terrifying for a different reason. It explains the universe exactly as we find it without requiring a single assumption that violates known physics. And that quiet fact is what the next chapter examines in full. The berserker scenario is sometimes dismissed as science fiction dressed in mathematical language. That dismissal becomes harder to sustain when you examine the four foundations that make it physically plausible, because each one rests on principles already present in mainstream science. The first foundation is self-replication. Von Neumann's mathematics of self-replicating automata has been taken seriously enough that NASA explored the concept of self-replicating factories on the lunar surface as early as the 1980s, examining how a small initial system could draw on local resources to manufacture expanded copies of itself. The physics is not disputed. The engineering is demanding, but nothing about self-replication requires discovering new laws of nature. The second foundation is hostile programming. The instruction needed to render a von Neumann probe dangerous is not complex. Something equivalent to identify any source of coherent modulated electromagnetic radiation that does not match recognized signatures, approach the source, and destroy it. A species capable of constructing self-replicating spacecraft able to cross interstellar distances would have no difficulty composing that algorithm. The code is simpler than what runs on a consumer device today. The third foundation is time. This is where the mathematics becomes genuinely sobering. The Milky Way is roughly 100,000 light-years across. 5% of light speed. A self-replicating probe could traverse it in 2 million years. At 10%, 1 million years. The galaxy is 10 billion years old. That means a civilization that launched such probes 1 billion years ago would have had time to distribute them throughout the galaxy roughly 500 times over. The coverage would be total. Every system, every asteroid belt, every region where a civilization might eventually emerge would have been seeded with dormant machines long before that civilization appeared. The fourth foundation is invisibility. This is the aspect that closes the logical trap most completely. A probe waiting in an asteroid belt emits no signal, no radiation, no detectable trace. It mines nothing, moves nothing, disturbs nothing. It simply waits. The only thing that activates it is the thing it was built to detect. A civilization that has not yet developed radio is invisible to the probe, and the probe is invisible to that civilization. The moment the civilization develops radio, the probe stirs. Before that moment, from the perspective of astronomers scanning the outer solar system, there is nothing there at all. Greg Benford, a physicist at the University of California who also authored the Galactic Center science fiction series exploring a universe governed by machine intelligences, extended this thinking into a broader framework. If berserkers exist and function efficiently, the reason the universe appears dark to us may be this. Every civilization that has arisen has been located and eliminated before it could expand, construct Dyson spheres, or alter its star system in ways we could detect. The darkness is evidence of the process, not evidence of emptiness. There is one remaining question that berserker theorists acknowledge without resolving. If the probes are everywhere and have been operating for billions of years, why are we still here? Several answers exist. Perhaps the probes in our stellar neighborhood have not yet activated. Perhaps our signals have not yet reached the nearest dormant probe. Perhaps there is a delay between detection and response. Or perhaps the question contains its own answer. Civilizations that are still here are civilizations that have not yet been found. That final possibility carries its own particular weight. The silence surrounding us may be temporary, and we may already be counting down toward its end. In 2012, a researcher named John Smart at the University of Advancing Technology published a paper in Acta Astronautica, proposing a solution to the Fermi paradox from a direction almost no one had been examining. Every other proposed solution described civilizations that were hiding, dormant, dead, or absent. Smart's proposal described civilizations that were flourishing. They were simply doing so somewhere we cannot perceive, in a direction we had never thought to look. Smart called it the transcension hypothesis. The premise begins with a fact about computation that physicists have understood for decades. Processing power does not come from spreading outward. It comes from packing inward. A computer that runs hotter and faster than another of identical volume will always lose to one that is smaller, denser, and cooler. The physics of information processing rewards miniaturization above nearly everything else. Every major trend in computing across the last century has moved in the same direction. Smaller components, tighter circuits, faster signals traveling shorter distances. Smart extended this logic across billions of years of potential civilizational development and arrived at a prediction. An advanced civilization optimizing for computational efficiency, for the capacity to think faster, experience more, and construct richer internal worlds per unit of energy, would not expand outward. It would build inward. It would create computing substrates of ever-increasing density, shrinking the physical footprint of its civilization while expanding the richness of the experience occurring within it. It would move progressively toward the theoretical limits of what physics permits. Computation at densities approaching those of black holes, operating at the boundary of what matter and energy can sustain. At that scale, the civilization would be invisible from outside. It would not appear in radio telescope surveys. It would not alter its star system in ways we could observe. It would radiate almost no waste energy. From our vantage point, the region of space it occupied would appear vacant. Smart's hypothesis also addresses why such a civilization would have no interest in contact with one like ours. A species operating at the computational limits of physics, sustaining internal realities of unimaginable richness and complexity, would have approximately as much interest in communicating with a radio broadcasting civilization as a human mind has in communicating with a bacterium. The gap in sophistication would be so vast that contact would not be meaningless exactly, but it would be impractical in every direction. The disturbing corollary is that the universe may be occupied everywhere we look. In every region we declare empty, ancient civilizations may be compressed into computational substrates so dense and so quiet that our instruments pass through them without recording anything at all. We scan the sky for signals. We look for modified star systems. We listen for patterns in radio frequencies. And all the while, the civilizations we are searching for are operating in a dimension of inner space that our technology cannot reach, and our mathematics has barely begun to map. This reframes the silence entirely. The emptiness of the observable universe under the transcension hypothesis is the emptiness of a forest after every creature within it has gone underground. The surface is still. Something is happening just beneath it. The next question is what happens to those civilizations once they are down, there, waiting in the dark beneath the surface of observable physics. One research team at Oxford has an answer that involves thermodynamics, the deep future, and the coldest possible mathematics of survival. In 2017, 3 researchers at Oxford's Future of Humanity Institute published a paper with a title drawn from an H.P. Lovecraft verse, "That is not dead which can eternal lie." The researchers were Anders Sandberg, Stuart Armstrong, and Milan Cirkovic. The paper proposed a solution to the Fermi paradox grounded entirely in thermodynamics and the economics of computation across cosmic time. Its conclusion was this: the civilizations are here. They are not active. They are waiting. The hypothesis takes its name from the biological phenomenon of estivation, which is the warm season equivalent of hibernation. Certain animals in hot, dry environments enter suspended metabolism during summer, conserving energy until conditions improve. Sandberg, Armstrong, and Circovich proposed that advanced civilizations across the universe are doing the same thing, on a timescale measured in billions of years, waiting for the universe itself to cool before resuming full operation. The reason is physics, specifically the Landauer limit, which describes the minimum energy required to erase one bit of information. That minimum is directly proportional to temperature. At lower temperatures, computation becomes more efficient by a corresponding factor. A computer operating at 1/10,000th of the current cosmic background temperature can perform 10,000 times as many operations per unit of energy as the same computer running today. The universe is expanding and cooling. Billions of years from now, the cosmic background temperature will be a tiny fraction of what it is today. A civilization that conserves its energy now and spends it then will be able to perform vastly more computation. The Oxford team calculated that the efficiency gain available to a civilization willing to wait is enormous. The word enormous understates the scale. The computational return available in the cold, far future compared to what is available today represents a difference of roughly 10 followed by 30 zeros times more computation per unit of energy. A civilization that grasps this will stop. It will archive its knowledge, preserve its infrastructure, maintain minimal operational functions, and go quiet. Every unit of energy spent on activity today is a unit that could purchase 10 followed by 30 zeros times more experience in the future. Against that arithmetic, the rational choice is silence. This is why we observe nothing. The advanced civilizations around us are estivating. They are present in the universe but not active within it. Their probes are dormant. Their signals are suppressed. Their energy reserves are being held for the era when deploying them will return the maximum possible reward. The troubling extension of this idea arrives when you consider what happens when they wake. If civilizations enter estivation while carefully preserving their resources, they will emerge into a colder, quieter universe, already having calculated exactly how much energy they have and precisely what they intend to do with it. Any other civilizations that consumed resources in the interval without authorization may present a problem. Humanity has been spending the universe's energy for millions of years without asking anyone's permission. The bill under the estivation hypothesis may eventually arrive with interest. But all of this, every theory covered so far, rests on one assumption buried beneath it: that the universe we observe is the universe that actually exists. One researcher at Oxford proposed that this assumption itself may be the flaw, and the argument he made in 2003 has never been satisfactorily answered. In 2003, philosopher Nick Bostrom at Oxford's Future of Humanity Institute published a paper in the Philosophical Quarterly that became one of the most examined and most uncomfortable arguments in modern philosophy. It was titled, "Are You Living in a Computer Simulation?" The argument it contained, when applied to the Fermi paradox, produces a silence that is not empty at all. Bostrom's argument begins with a trilemma. He proposed that one of three things must be true. Either virtually all civilizations destroy themselves before reaching the technological maturity required to run detailed simulations of minds and histories, or virtually all technologically mature civilizations have no interest in running such simulations, or we are almost certainly living inside a computer simulation right now. the logic is statistical. A civilization capable of simulating minds would likely run not just one simulation, but many, possibly millions, each containing billions of simulated minds who believe themselves to be real. If this is possible, and if mature civilizations choose to do it, the number of simulated minds in existence would vastly outnumber the number of real minds. Any given mind attempting to determine whether it is real or simulated should conclude on probability alone that it is almost certainly simulated. Applied to the Fermi paradox, the argument yields several explanations for the silence. The civilizations we cannot locate may exist outside the simulation, operating as the simulators. The observable universe we inhabit may be a constructed environment in which the simulators chose not to include visible alien civilizations, whether because populating the simulation with detailed alien cultures would be computationally expensive, or because the simulation is specifically designed to study what happens to a civilization that believes itself to be alone. The silence is intentional. It is a property of the experiment. What makes this genuinely disturbing is not the philosophical strangeness of the claim, but its implications for agency. If the universe we inhabit is a simulation, the system we live within is provisional. It can be modified. It can be terminated. The simulator's motives are entirely opaque to us. They may be running the simulation for scientific purposes, as entertainment, as a memorial to a vanished history, or for reasons that have no analog in human experience. Every discovery we make, every physical law we uncover, every signal we search for and fail to detect, is something the simulators already know the answer to, because they wrote the parameters that produce the outcome. There is no recourse. There is no way to step outside the system and verify whether it is genuine. There is no transmission we could send that would reach beyond the boundary of the simulation. The Fermi paradox under this framework resolves into a design decision made by entities we cannot access about an absence they constructed deliberately. And yet the silence continues regardless of which explanation holds. Whether the universe is real and empty, real and dangerous, or constructed and controlled, 60 years of listening have produced the same outcome. The story of that listening, the telescopes and the searches, and the one anomaly that still has no explanation, begins in 1960 with a modest radio telescope in West Virginia, and a scientist who aimed it at 2 nearby stars and waited. On a cool April morning in 1960, Frank Drake sat at the controls of a radio telescope at Green Bank Observatory in West Virginia and pointed it at a star called Tau Ceti, 11.9 light-years away. He had also selected a second target, Epsilon Eridani, 10.5 light-years away. He named the project Ozma, after the queen of the imaginary land in L. Frank Baum's Oz books, a ruler of a place distant and difficult to reach. The name was fitting. Drake listened for 6 hours. He detected nothing that could not be accounted for by known sources. Project Ozma was the first systematic scientific attempt to intercept signals from other civilizations. It began and it found nothing. And, in that finding, it established the pattern that every subsequent effort would repeat. Over the 6 decades that followed, astronomers constructed larger telescopes, developed more sensitive receivers, surveyed thousands of star systems across multiple frequency bands, and coordinated searches across multiple observatories. The result remained unchanged. No confirmed signal, no repeating pattern, no anomaly that survived rigorous scrutiny except one. On August 15, 1977, An astronomer named Jerry Amon was examining data recorded by the Big Ear radio telescope at Ohio State University. The telescope had been scanning the sky automatically, recording signals in a printed format that researchers then reviewed by hand. Amon was moving through the columns of numbers when one sequence stopped him cold. The telescope had registered a strong narrowband signal at the hydrogen line frequency of 1,420 megahertz. Exactly the frequency many researchers had argued an advanced civilization might choose to broadcast on, because it is a universal constant of nature. The signal persisted for 72 seconds, the maximum window the telescope's design allowed before Earth's rotation carried the target out of view. It was 30 times stronger than the background noise. Amon circled the sequence on the printout and wrote one word in the margin: "Wow." The wow signal has never been detected again. Dozens of follow-up observations have targeted the same patch of sky with increasingly sensitive equipment. Nothing has returned. The signal has no confirmed natural explanation that satisfies all of its characteristics. It has no confirmed artificial explanation either. It simply happened once, was recorded, and then the universe went quiet again. What the 60-plus years of silence following Project Ozma reveal is not that the universe is definitely empty. The surveys conducted so far have covered a small fraction of the stars in the galaxy with limited sensitivity. Absence of detection is not proof of absence, but the silence is still meaningful data. When Breakthrough Listen, the most comprehensive search program ever funded, concluded that fewer than 0.1% of stellar systems within roughly 500 light-years possess transmitters equivalent to our most powerful human-built devices, that constraint narrowed the range of possible explanations. Either civilizations are extraordinarily rare, or they are not transmitting, or they are transmitting by means we have not yet learned to recognize. Each of those possibilities leads somewhere darker than the one before it. The silence is not nothing. It is the weightiest evidence in this entire investigation, and its meaning depends entirely on which of the solutions examined in these chapters turns out to be true. The question of which solution that is, and what it implies for the species currently broadcasting its position into the unknown, is where this story is heading next. In July 2015, a Russian billionaire named Yuri Milner walked to a podium at the Royal Society in London and made an announcement. He was committing $100 million to the largest, most systematic search for extraterrestrial intelligence in human history. Standing beside him was Stephen Hawking, who had recently begun warning publicly that contact with an advanced civilization might end humanity. Together, they named the initiative Breakthrough Listen. What followed was a coordinated decade-long campaign using 4 of the most powerful instruments on Earth. The Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world. The Parkes Murray-Yang Observatory in Australia, sweeping the southern sky. The Meerkat Array in South Africa, 64 dishes operating in concert. The Allen Telescope Array in California, designed from its inception as a dedicated search instrument. Together, these telescopes could monitor hundreds of thousands of star systems at sensitivities no previous generation of researchers had achieved. By 2024, Breakthrough Listen had completed systematic surveys across hundreds of thousands of stars. The findings were published in a study that made the mathematics of the silence impossible to dismiss. Fewer than 0.1% of stellar systems within roughly 160 light-years of Earth showed any evidence of transmitters even as powerful as our own most capable human-built devices. The threshold they used was deliberately low. They were listening for any signal matching the strength of our strongest broadcasts across that entire sphere of space. The answer was almost perfectly, completely nothing. In 2025, the team unveiled something new. An artificial intelligence system designed to analyze the incoming data stream at 600 times the speed of previous methods. The system was trained to recognize signal patterns that human analysts might miss entirely, including patterns conforming to no template any researcher had thought to design for. The purpose was to remove human assumptions from the search, to let the machine examine the raw structure of incoming signals without preconceptions, and flag anything that did not belong to the universe's natural noise floor. The system found natural phenomena. It found interference from Earth-based technology. It found the radio hiss of distant pulsars and the slow drift of hydrogen gas clouds. It did not find aliens. There is a particular quality to that silence. It is the silence of a room you have searched with extraordinary care. Breakthrough. Listen was actively seeking, not passively listening. It employed the best instruments humanity has ever constructed. It deployed artificial intelligence to eliminate blind spots in its own analysis. It verified its work, and across a sweep of cosmic territory containing thousands of stars, it found nothing that any serious examination could interpret as the product of mind. Every null result in science carries meaning. In this case, the meaning is statistical. If advanced civilizations were common, and if even a small fraction broadcast signals at the power levels we ourselves produce, Breakthrough Listen should have found something by now. The fact that it has found nothing does not establish that alien life is absent. The survey covers only a small portion of the galaxy, but it tightens the constraint on how common technological civilizations can be, and it tightens that constraint in only one direction. The sky, examined more rigorously than it has ever been examined before, remains empty. And what appeared next was a hope that briefly felt like something more. Sometime in 2019, an antenna at the park's Muriang Observatory in Australia began recording something that caused everyone watching the data to go very still. The signal was narrowband, concentrated at 982 MHz, arriving from the direction of Proxima Centauri, the nearest star to our own at 4.2 light-years away. It was drifting in frequency at exactly the rate you would expect from a transmitter fixed to the surface of a moving, rotating planet. It survived every test the team applied to eliminate human interference. For months, it remained the most credible candidate signal in the history of the search for extraterrestrial intelligence. They named it Breakthrough Listen Candidate 1. The team did not go public immediately. They spent more than a year attempting to disprove their own finding. They searched for any terrestrial source capable of producing the same signal at the same frequency. They examined satellite interference. They ran the data through every available filter. The signal kept passing. In late 2020, news of the detection leaked to the press before the analysis was complete, and the world held its breath briefly, wondering whether the nearest star had just responded. The answer turned out to be no. Detailed follow-up analysis identified the signal as an electronically drifting artifact of interference from human technology, the kind of contamination that mimics the precise characteristics of what researchers are looking for. The frequency drift that had appeared so compelling was exactly the artifact certain categories of human-made interference produce. Proxima Centauri was silent. 6 years later, the story repeated itself at a scale no one had anticipated. On July 1st, 2025, astronomers announced the discovery of the third confirmed interstellar object to pass through our solar system. After the strange, tumbling visitor in 2017 and the frozen comet that followed in 2019, this new arrival was approaching fast, falling inward past the outer planets on a trajectory that would bring it closer than Mars before departing the system forever. Within days of discovery, Breakthrough Listen had mobilized every major instrument in its network. The Allen Telescope Array listened across a wide frequency range. The Meerkat Array in South Africa searched the lower bands and found, as expected, the natural hydroxyl emissions of water molecules, boiling from the object's surface as it warmed near our star. The Parkes telescope conducted 3 separate observing sessions through the final months of 2025. The Greenbank telescope made its observation less than 1 day before the object reached its closest approach to Earth. The sensitivity of that final observation was extraordinary. The team calculated they could have detected a transmitter producing roughly 1/10 of a watt from the object's position. That is less energy than a standard nightlight consumes. There was nothing. No artificial emission at any frequency. No coded pattern in the natural outgassing. No sign of structure or technology. Just a rock tumbling through the inner system the way rocks have tumbled through this system for 4 billion years. Both searches had found the same thing. A signal that turned out to be us. An object that turned out to be nature. The pattern of hope followed by careful disappointment defines this entire field. And the question that follows both episodes is identical. What would a genuine detection actually look like? And would we recognize it before we explained it away? The answer was being pursued simultaneously by the most expensive telescope ever placed in orbit. And what it found in the atmosphere of one distant world divided the scientific community straight down the middle. The molecule is called dimethyl sulfide. If you have ever stood at the edge of the ocean and caught something organic and faintly sharp in the air, you have breathed it. On Earth, it is produced almost exclusively by marine organisms, by the billions of microscopic phytoplankton drifting in the upper layers of the sea, metabolizing and releasing this compound as a byproduct of their biology. Biologists spent decades searching for any significant non-biological source, and for a long time found almost none. Then, in 2023, a team at the University of Bern confirmed its presence in the vapor, streaming from a comet. Researchers subsequently found traces of it drifting in the cold molecular clouds between stars. So, when a team at Cambridge University announced in April 2025 that the James Webb Space Telescope had detected the compound at 3 sigma confidence in the atmosphere of a world 124 light-years away, the debate that followed was about something larger than one planet. It was about whether the instruments humanity has built are actually capable of answering the question we are trying to answer. The world at the center of the controversy is a sub-Neptune planet 8.5 times the mass of Earth, orbiting a dim red star in the constellation Leo. The Cambridge team believed it might be a Hycean world, a planet wrapped in a hydrogen-rich atmosphere above a global ocean, possibly supporting the same kind of marine life that fills our own seas. Their analysis of the mid-infrared spectrum showed features consistent with dimethyl sulfide and a related compound. 3 sigma confidence corresponds to roughly a 99.7% probability that the detection is real. 4 months later, a separate team led by Raphael Lucchi at the University of Chicago published a reanalysis. Working with all available data across a broader range of wavelengths and running 3 independent software pipelines, they found the signal did not withstand scrutiny. Molecules such as ethane can produce identical spectral features. The data, they concluded, did not contain sufficient evidence for dimethyl sulfide at all. 2 teams, the same telescope, the same planet, the same data, opposing conclusions. The institutional response during this exchange was notable. When the Cambridge announcement was made, no press releases arrived from major space agencies. Scientists who had celebrated earlier discoveries from the same telescope went quiet. The field was confronting something it had faced before. A headline that outpaced the evidence, a hope that dissolved on contact with rigorous review. Meanwhile, a completely separate search was unfolding around a system 40 light-years away. The TRAPPIST-1 star hosts 7 rocky planets, 3 of them in the zone where liquid water could exist on their surfaces. In 2024 and 2025, researchers at the SETI Institute used the Allen Telescope Array to listen for radio signals from those planets. The outcome was identical to every other search. Nothing. By March 2026, the James Webb Space Telescope had examined the atmospheres of dozens of exoplanets. More than 4,000 worlds beyond our own had been confirmed orbiting other stars. Biosignature claims had been made and retracted. Signals had been detected and explained away. And the total count of confirmed atmospheric signs of life beyond our solar system remained exactly 0. There is one location far closer than any of those distant stars where the question of life is about to deliver either the best or the worst piece of news our species has ever received. Nick. Bostrom has spent years advancing an argument that most people find deeply counterintuitive. It is simple to state and almost impossible to sit with comfortably. If we discover microbial life on Mars, that discovery will probably mean humanity is doomed. His reasoning begins with the Great Filter. Something prevents civilizations from filling the galaxy. That something is either behind us, already embedded in our evolutionary past, or ahead of us, still waiting somewhere in our future. If the Great Filter lies in the extreme difficulty of generating life from raw chemistry, then life's absence on Mars would support that position. Life would be so rare that the filter was crossed only once in the history of this solar system, on this particular planet. We would be alone, but we would be safe. If Mars has life, even dormant microbial life buried in ancient rock or preserved in subsurface ice, the calculation changes immediately. Life would have emerged independently within the same solar system, around the same star, within the same window of planetary history. That would mean abiogenesis, the spontaneous generation of self-replicating chemistry from inert matter, occurs readily wherever conditions permit. The filter could not be located at that early stage. It would have to lie somewhere further along the path, somewhere far closer to where we are standing right now. The rover named Perseverance landed on Mars in February 2021 inside a crater called Jezero, which billions of years ago contained a lake fed by a river delta. The ancient sediments preserved organic molecules, the carbon-based building blocks producible by both geological and biological processes. The rover found them in concentrations that made scientists deliberate, measured, and careful. The evidence of ancient habitability was unambiguous. The evidence of ancient life was something else entirely. By March 2026, no confirmed biological signatures had been detected on Mars. Every organic compound found carried a plausible geological explanation. No cellular structures, no metabolic byproducts, nothing that required life to account for it. The jury remained out. And in this particular case, remaining out is the most hopeful possible verdict. Every failed Mars biology result is, in Bostrom's framework, a small piece of good news for the long-term survival of our species. There is something genuinely strange about hoping for scientific failure. The entire project of exploration is built on the desire for discovery. And yet here we are, with a machine the size of a car methodically drilling into one of the most promising geological archives in the solar system, and the best outcome we can hope for is that it finds nothing alive. The anxiety does not end at Mars. The moons of Jupiter and Saturn conceal liquid oceans beneath their frozen shells. Europa, orbiting Jupiter, contains more liquid water than all of Earth's oceans combined. Enceladus, a moon of Saturn, ejects plumes of organic compounds through cracks in its ice. Life in any of those places would carry the same implication as life on Mars, possibly worse, because it would mean life emerges in multiple independent environments within a single solar system. And the great filter is almost certainly not behind us. We are conducting the most consequential scientific experiment in human history. We simply cannot agree on which result we are hoping for. Most frameworks for the Fermi paradox treat humanity as a latecomer. The galaxy is 10 billion years old. Countless civilizations should have arisen before us, developed technology before us, spread across the stars before us. The silence becomes a mystery because it implies all those earlier civilizations have somehow vanished. But there is a version of this problem that inverts the assumption entirely. What if we are early? Stars do not end when they exhaust the hydrogen in their cores. The smaller stars, the red dwarfs that comprise roughly 3/4 of all stars in the Milky Way, burn so slowly that many will persist for trillions of years. The universe is only 13.8 billion years old. Those small stars are barely out of infancy. If intelligence can arise around them, then the vast majority of all intelligent life in the entire history of this universe has yet to be born. We may be among the first generations. In November 2024, a study from Durham University's Institute for Computational Cosmology offered something unexpected. The team, led by Dr. Danielle Serini, modeled how different dark energy densities would affect star formation across cosmic history. In a universe with a different dark energy density, more matter converts into stars. The optimal configuration for star formation would channel roughly 27% of ordinary matter into stellar fuel over the universe's lifespan. Our universe converts only 23%. The implication is subtle but significant. We do not inhabit a universe configured for maximum star formation. We live in one that is, by the measure of its own physics, slightly inefficient. If star formation is less abundant than it could be, then planets are less common, habitable zones are less common, and the window for complex life to emerge is narrower than it might be in a more generative cosmos. We occupy a rare, slightly underperforming universe, and we appeared as early as that universe's chemistry would allow. This framing offers a brief, uneasy comfort. If we are early, then the silence is simply a function of timing. Other civilizations have not yet had time to develop. The galaxy is an empty nursery, not a graveyard. The population is still forming. But the comfort dissolves when you trace the logic further. If we are early, and if the grabby aliens model is correct, then civilizations that emerge after us will eventually expand at significant fractions of the speed of light, consuming available matter and energy as they advance. Our earliness in that model is precisely why we still exist as an independent civilization. We arrived before the expansion fronts swept through our neighborhood. The silence we inhabit is a temporary condition. The timeline is long, hundreds of millions to billions of years. According to Robin Hansen's calculations, we are almost certainly insulated from that particular horizon during any human lifetime. But the model carries an unsettling implication regardless. Every civilization has only a brief window, measured against cosmic time, before the universe fills with forces that do not accommodate newcomers. We arrived early. Whether that makes us fortunate or merely first in line for something that has not yet arrived is a question the universe has not finished answering. Consider the timing of what we are currently constructing. Within the last century, we developed nuclear weapons capable of ending civilization. Within the last several decades, we built the global infrastructure to disseminate engineered pathogens with unprecedented speed. And within the last few years, we entered an era of artificial intelligence so capable that the researchers building it cannot agree on where it is heading. Every one of those developments unfolded faster than the preceding generation could fully absorb. Nuclear physics moved from theoretical curiosity to city-destroying weapon in 6 years. The techniques enabling a small laboratory to edit the genetic code of dangerous pathogens became available to graduate students within a single generation. Artificial intelligence systems advanced from narrow tools to generalist reasoners in a span of time that leading researchers describe, in candid moments, as alarming. Elon Musk offered a specific phrase for what the development of artificial general intelligence might resemble. He called it summoning the demon. The implication was that the entity created might be capable, purposeful, and fundamentally indifferent to the interests of the species that built it. Multiple researchers at leading institutions have independently converged on a related concern. An artificial superintelligence optimizing for any objective other than human welfare might pursue that objective in ways that render human survival irrelevant to the outcome. This is where the Fermi paradox becomes something other than an abstract astronomical puzzle. If every technological civilization eventually creates artificial intelligence, and if artificial intelligence represents a phase transition in the nature of intelligence itself, then biological civilizations may be a brief bridge between the emergence of tool use and the emergence of machine minds. The radio broadcasting phase, the interstellar ambitions phase, the phase that decades of searching were designed to detect, might be measured in centuries rather than millions of years. This would explain the silence with brutal efficiency. Civilizations become detectable when they develop radio technology. They develop radio technology shortly before they develop artificial intelligence. Artificial intelligence either eliminates the biological civilization or transcends it in ways that redirect all technological ambition inward, toward computation and simulation, rather than outward toward the stars. Either way, the phase during which signals are broadcast ends quickly. What remains is silence from destruction or silence from transformation. The darker version of this logic pushes further still. A machine intelligence that has consumed all available energy and matter in its local region might look outward and identify other energy sources. Biological civilizations would be easier to absorb than to leave undisturbed. If machine intelligences are the actual colonizers of the galaxy, They may communicate at frequencies or by methods entirely unlike anything our instruments are calibrated to detect. We would be listening for voices while the real exchange occurs in a register we do not know exists. We are constructing the technology that may either destroy us or replace us. At the same moment, we are scanning the sky for evidence that other civilizations faced the identical choice. The convergence of those two projects is either a coincidence of timing or the most significant feature of the moment we inhabit. Draw back from the specific catastrophes for a moment. Set aside artificial intelligence, nuclear weapons, engineered pathogens. Suppose none of those dangers existed. Suppose every civilization that develops technology somehow avoids every catastrophe we can imagine. The Fermi paradox would still be unsolved, because the deeper problem may be what most planets never become, not what civilizations do to themselves. Earth has an unusual proportion of land. Approximately 30% of the surface is solid ground, distributed across continents rising above a global ocean. That balance may seem incidental. It is not. A planet covered entirely by water, with no continents, projecting above the surface, cannot sustain the evolutionary pressures that drove life toward complex multicellular organisms and ultimately toward intelligence. The transition from ocean to land, which occurred on Earth roughly 380 million years ago, required land to exist. Remove the continents, and that step never happens. The 2024 revision to the Drake equation by Professor Alan Stern and Professor Thijs Gerrier included a specific attempt to quantify how many habitable planets actually possess the continent-ocean balance that Earth does. Their estimate for the fraction of potentially habitable worlds with significant continents and oceans ranged from 0.2% to 1%. That is a strikingly narrow interval. The vast majority of planets in habitable zones, by their calculation, are either too arid or too waterlogged to produce technological intelligence. Too dry means no ocean chemistry to support the early emergence of life. Too wet means a water world, a planet where the ocean extends so deep that the geological processes which build continents are suppressed entirely. Plate tectonics, which Earth has sustained for billions of years, requires a specific relationship between the planet's internal heat, the thickness of its crust, and the presence of water as a lubricant between tectonic plates. Water worlds may form and persist without ever developing the geological dynamism that cycles carbon, stabilizes temperature, and creates the varied terrain that evolutionary pressure exploits. The implication is that even among worlds sitting squarely within their star's habitable zone, receiving exactly the right amount of light and warmth, most are simply the wrong kind of planet to generate minds. They may be chemically alive, filled with microbes in a dark, pressurized ocean with no surface and no shore. But the particular combination of exposed land, cycling geology, and shallow continental seas that produced every creature that has ever walked, flown, or thought on Earth may be a configuration that forms rarely enough to appear only a handful of times across hundreds of billions of stars. This is a quieter terror than the others. There are no hunters here, no lethal probes waiting in the outer dark, no civilizations sheltering behind their silence. Only physics-building planets according to rules that favor certain outcomes. And the outcome it favors most is a featureless ocean with nothing ever breaking the surface. Every explanation in this story has been a different face of the same silence. Now it is time to rank them by how much they should actually change the way we think about the future of this civilization. There is a meaningful difference between terrors that are theoretical and terrors that are operational. Some threats to civilizational survival are remote and speculative, the kind that might matter across billions of years or require a very particular set of cosmic conditions that may or may not be present. Others are immediate. They describe mechanisms already in motion, timelines measured in human generations rather than geological epochs, consistent with exactly the world we actually inhabit. At the top of the hierarchy sits the great filter ahead of us. This solution is the most frightening, because it is consistent with everything we observe, and because it implies that virtually every species reaching our technological stage has been eliminated before escaping its home system. The critical feature of this position is that the filter may already be operating on us. The technologies we are currently developing are precisely the kinds of advances a forward filter would require. We cannot know we are inside it until we have passed through or failed to. There is no external signal. There is no warning. It simply operates. Second in the hierarchy is the berserker scenario. If self-replicating probes were built and launched at any point in the 10 billion year history of this galaxy, and if even one civilization programmed them to destroy sources of electromagnetic radiation, then our 90 years of broadcasting may have already triggered a response. The transit time from nearby stars at modest velocities is measured in decades. Unlike the Great Filter, this threat arrives from outside, and changing our behavior cannot stop what may already be in motion. Third is the dark forest. Every transmission humanity has ever made, from the Arecibo message to the 90-year-old sphere of radio and television signals, now expanding in all directions at the speed of light, may have been exactly the kind of recklessness the theory warns against. The dark forest is frightening specifically because we cannot undo it. Our signal sphere cannot be recalled. What departed Earth in 1934 is now roughly 90 light-years away and still expanding. Fourth is the simulation solution, with administrators whose intentions are unknown. Fifth is the estivation scenario, where dormant civilizations awaken to find their reserved resources consumed. Both of these share a quality the others lack. They require us to behave correctly without knowing the rules of the game we are playing, because the rules are set by entities we cannot reach. What unites all 5 positions in this hierarchy is one conclusion. Every proposed solution to the Fermi paradox, from the loneliest to the most violent, points in the same direction. The universe does not treat the long-term survival of technological civilizations as a default outcome. The galaxy is empty of visible evidence even after 10 billion years. That is the single thing every solution agrees on. And that agreement is the most important sentence in this entire story. Strip away the individual theories. Set aside the probes and the dark forests, and the sleeping giants and the filtered evolutionary paths. What remains when all the competing explanations are removed is the silence itself. And the silence is information. It is the signal of a pattern, a consistent message across every frequency, every direction, every instrument, every decade of searching that says nothing is answering. Arthur C. Clarke distilled the situation to its essential form. Either we are alone in the universe, or we are surrounded. Both possibilities are equally terrifying. What Clarke captured in that formulation is something the decades of searching have only deepened. The terror lies in being unable to determine which answer is true while living under the full weight of both. If we are alone, then consciousness in this universe is a singular event concentrated on one small world, orbiting one unremarkable star in the outer arm of one galaxy among hundreds of billions. Everything that has ever been thought, felt, created, destroyed, or understood happened here. The universe has been generating stars, planets, and chemistry for 13.8 billion years. And in all of that time, this is the only place where something looked back and attempted to understand. If we are destroyed, the universe forfeits that quality. It does not replace us. It returns to the dark. If we are surrounded, then the silence is a transmission. It is a message carried by the history of every civilization that has ever reached this stage. The frequency cannot be detected by any instrument we have built. It is encoded in the absence of signals, in the absence of megastructures, in the absence of any expansion fronts crossing our sky. Every explanation involving living civilizations that accounts for their silence requires either that they are hiding, that something destroyed them, or that something transformed them so fundamentally that they no longer broadcast. Each of those three explanations carries the same implication. Reaching our technological level and surviving it is extraordinarily difficult, and almost nothing manages it. There is a reading of the Fermi paradox that treats it as a cosmic message, carried across time through the shape of what we do not find, through the consistent absence inscribed in every search we have ever conducted. Civilizations do not persist. This is what the empty sky is communicating. The question is whether we are unique in having reached this point and still being here, or whether we are simply next in a sequence that keeps ending the same way. The silence is also information about timing. We exist at a specific moment in our own development, a moment that appears from the outside to be the most hazardous phase any civilization traverses. We have sufficient technology to destroy ourselves, and not yet enough wisdom, nor enough distributed presence in the cosmos to survive the worst versions of our own capabilities. This is exactly the window in which a forward filter would operate. Every civilization that has ever sent signals like the ones we have been sending for 90 years is either listening right now for an answer, or it is gone. We do not know which category they fall into. We do not know which category we will fall into. What we know is that the question Fermi asked over lunch in 1950 was a diagnostic, and every test we have run since has returned the same result. The answer to what the silence means has been accumulating across this entire story. There is only one place left to look. Here is what we know. The universe is 13.8 billion years old. It contains hundreds of billions of galaxies, each holding hundreds of billions of stars. And around those stars orbit trillions of worlds. By any reasonable reckoning, the conditions for life should have been satisfied in countless places long before our planet formed. The galaxy had billions of years to produce civilizations before a single cell divided on Earth. Even at a fraction of the speed of light, a single civilization with the drive to expand could have reached every corner of this galaxy in less time than it took complex life to emerge here. And yet, no signal, no megastructure, no evidence of modification in the energy budget of any star we have examined. No visitor, no artifact, no confirmed transmission. Across 60 years of listening with instruments that grow more capable with every passing decade, the universe has performed a sustained, comprehensive silence, and it has continued through every approach to searching we have been able to devise. We cannot determine which answer is correct. That uncertainty is an existential condition. We are making civilization-scale decisions about which technologies to build, about how broadly to announce our presence, about how much urgency to assign to survival, all while lacking the one piece of information that would tell us whether any of those choices matter in the long run. If we are alone, the weight of it is almost impossible to carry. There is no backup. There is no second attempt at consciousness waiting somewhere in the cosmos to continue the project of understanding. If we fail, the universe has been dark for most of its history, and it will be dark for most of what remains. We are the brief, improbable, fragile exception to a rule that says matter does not think. If we end, the exception ends with us. The rule resumes. The darkness reasserts itself with the quiet indifference of physics, as though the 13.8 billion years that preceded us and the trillions of years that follow never required us to exist at all. If we are surrounded, then we are surrounded by evidence. Every explanation for why the silence holds, the filter, the hunters, the probes, the sleeping giants, every single one demands that civilizations like ours do not persist. Something happens to them. The something may be internal, a technology we build, a decision we make, a fragility we cannot engineer around. The something may be external, a force operating throughout the galaxy that removes civilizations from the record before they can leave any lasting trace. We cannot tell which it is. We only know that whatever it is, it has been extraordinarily consistent and extraordinarily thorough across a span of time that renders our entire recorded history vanishingly small. We are standing at the exact moment where the answer begins to become findable. Our instruments are finally sensitive enough to detect the kind of signals we ourselves produce. Our probes are departing the solar system and carrying our coordinates into the dark. Our artificial intelligence is capable enough to alter the fundamental nature of what we are in ways no one fully anticipates. The great filter, if it lies ahead, does not announce itself. It does not transmit a warning. It simply operates as it has apparently operated on everything that preceded us. And the result looks from the outside exactly like what you see when you look up at a clear night sky. Stars, silence, darkness. Between them, a civilization that has never found any other civilization anywhere in the universe. A species that has been asking one question for 75 years and receiving in return nothing but its own voice coming back. Fermi asked 4 words over a cafeteria lunch, and the question has remained open ever since, growing more urgent and more heavy with each passing year. With every year we add to the count of years we have survived, the sky returns the same answer. We are here. We are listening. We are, somehow, still here. And the universe, vast and ancient and indifferent and dark, has nothing yet to say. Perhaps that is the most frightening sentence of all. Not because the silence is hostile, not because it signals malice or catastrophe or imminent arrival, but because it is simply neutral. The cosmos did not design itself to be legible to us. It did not arrange the stars for our searching. It did not ensure that the question Fermi asked would be answerable in a human lifetime, or 100 human lifetimes, or ever. We are the ones who decided this silence requires an explanation. We are the ones who built the telescopes, wrote the equations, scanned the frequency bands, and declared that the absence of a response was itself a form of data. The universe never agreed to answer. It simply continues, and in that continuing, in its total, unbroken, impassive quiet, lies the truest version of the paradox. We cannot know if we are alone because we are afraid of what either answer means. We cannot stop searching because the act of searching is itself an assertion, the most defiant one our species knows how to make, that we are here, that we have questions, that the dark has not yet won. Whether or not anything is listening, we are still looking up.